Okay, let's take a look at Leetcode 239 sliding window maximum. So this is a pretty popular problem, and this algorithm, using an O of n time complexity in order to solve this is, it's pretty foundational, and a lot of other harder problems might actually tie into this problem. So I think it's pretty good to understand how to do this. So let's just look at the question, and I'll kind of go through a brute force solution, and then I'll describe how you can optimize it using a data structure called a deck. So you're given an input, and then you're given a window size. So you just go through the input array, and they want you to find the maximum value in each of those windows of size k. So if we look at this first example here, the first window of size k, which is 3, so the maximum in this window is 3, so that's why we output 3. The next window is, just shifted 1 over, and then the max in this new window is 3. Same thing with 5 here, and then 5 here, and then 6 here, and 7 here, right? So we're just finding the max value in each window of size k. So you should also note that the output size is not going to be the same size as the input, right? Because there's not going to be the same amount of windows of size k as there are in the input, as the length of the input, unless k is 1 or something, right? Because then you'd output, then each window size would just be each individual number. But yeah, as you can see, like you won't be outputting anything when you're at this 0th index. You won't be outputting anything when you're at this first index. You'll start outputting once you reach this index here. Once you reach this -1, then you know that you've reached a window size of 3, and then for each element after this -1, as you can see for -3, you'll continue to output the max value in that current window. So yeah, I mean, the brute force approach, you would just go through each window of size k, and then iterate through all the numbers, and just keep like a tally of the or just keep a variable to see which number is the maximum. And the problem with that is, let's say we look at window 1 here, which is 1, 3, -1, then we shift the window over by 1. We're going to have to reprocess the 3 and -1. So this approach could go up to n squared time complexity, which is not efficient. So let's see how we can solve this in O of n time with a data structure called a deck. And if you're not familiar with a deck, don't be overwhelmed by it. It's not that confusing. The way I think about it is I think of it as a special type of array or list where you can pop from the front in O of 1 time. So typically with a regular array, you can only pop off the back in O of 1 time, but with this deck, you can pop off both the front and the back in O of 1 time. And the reason you can do that is because the deck is actually a doubly linked list, and basically with a doubly linked list, you're able to delete faster. Okay, so let's kind of just walk through this example here, this first example here, and I'll show you how we're going to populate the deck and what its purpose is going to serve. So first, also I should mention that what our goal is with this deck is we're going to hold the maximum value of each window. So let's say the window we're looking at is 1, 3, -1. The max value in that window will be stored at the first element in this deck, always, right? So if we move the window to 3, -1, 3, our max value in this deck will still be 3. And then if we move the window over by 1 again, -1, -3, 5, the max value in our deck will be 5. So then at every time we need to output, we'll just output whatever is at the front of the deck. So let's see how we can maintain this deck in order to maintain that property of having the max value in that current window at the front of the deck. So let's just start over from here. Start with I at 0, and okay, so first thing we'll do is we'll input 1 into the deck, and I'll go through the different things that we have to do once we encounter them. So since there's nothing else in the deck, we just move onto the next index. And so before I move on to the next index, like I said, the front of the deck will always contain the max value in that current window, and the current window when we're at index 0 is just this value of 1. So the deck is holding the max value of this window in its first element, which is correct. So once we move the I over to the next index, we'll have the 3, so we can append that on. But then we see that since we're looking at the window of 1, 3, our max value in this window is actually 3. So in this case, we need to actually remove the 1. We need to pop the 1 off. So actually what we will actually be doing is we'll be popping off everything to the left of this current index that we're at. So basically we're just starting from the back, from the right, and we're popping off anything that is less than the current number that we're about to put in. So we'll pop off the 1 and then we'll put in the 3. And basically the way you can think about this is the deck should always be in decreasing order. Okay, so then let's move to the next index, because we finished looking at this window of 1, 3. So now we're going to be looking at the window of 1, 3, negative 1. So we're going to put in the number negative 1. And is the deck in decreasing order? Yes. So this is fine. And yep. So now we've finished looking at the first full window of size 3, right? So now we can actually output something to represent the max value in this window. And like I said earlier, the max value of this window is currently held in the first element of the deck. So we'll just output whatever is at the front of the deck, which is 3. Okay, and then now we'll move the I over to the next element, and first we'll just check, starting from the back of the deck, we'll check if the current element we want to put in is, if the current element we want to put in is greater than whatever is at the back of the deck, then we'll pop that off, but it's not. So that's why this negative 3 fits in at the end. And like I said, the property that the deck should remain in decreasing order is preserved here. Okay, so now we should also output another item to our output list, because now we're at the second window of size 3. So what is the max value of this second window? It is in fact 3, so that's why we're outputting the front of the deck again. Right, we're always going to output whatever's at the front of the deck. So now we're going to move the I to the next index, and now here is where things start to get a little bit, might get a little bit confusing. So basically, when we're at the 4th index, the window that we're looking at is negative 1, negative 3, 5. So that means this 3 is actually not in our window of size 3 anymore. We've already passed that index, and that index should not be included in our current deck. The deck will always store the max value of the current window, and 3 is not part of our current window, so it needs to be removed. But how do we know that the 3 is not part of our current window? So actually, although I've been using the number of values, these input values in the deck, actually the deck is actually supposed to be holding the indice numbers. So you can imagine it was actually supposed to be the indice of 1 here, indice of 2 here, indice of 3 here. And so basically you'll know when to remove if the indice at the front is less than or equal to I minus k. So like for example here, I is 4 and k is 3, so 4 minus 3 is 1. So is there any element indice in our deck which is less than or equal to 1? Oh, yep. So the first one here is less than or equal to 1. So we need to actually remove that from our window. So just remember that in the implementation. For now, I'm just going to show you the actual number of values in the deck. But when you implement it, the deck should actually be holding the indice values, the indice numbers, rather than the values. And with the indices, you can easily just use that indice in order to find the corresponding number value in the input array. That's as easy as just, taking whatever number, taking the indice and then just using that to find it in the array. Okay, so Yep, so then we're going to actually want to insert the 5 now. So after we've removed everything that isn't, in the current window range, then we can add the current number that we're processing, which is 5. So, but before we add the 5 onto the deck, we have to look at if the number before it was less than or greater than our current number we're processing. So it's actually less than the number we're processing. So that's why we have to pop this off. And then now we compare the -1 to the number that we want to insert, which is 5. And so 5 is greater than that as well. So we pop that off as well. And now 5 is the only one left in our deck. And the reason we do that is because in this window, -1, -3, 5, our largest value is 5. And we want to have 5 at the beginning of our deck. So that's why we had to remove the -1 and -3 in order to maintain the property of a decreasing order in our deck, aka having the max value at the front. So now after we've put in the number, then we should output something. So we'll always just be outputting whatever's at the front of the deck, which is 5. So as you can see from their defined answer, we're already on a good track. We have 3, 3, 5 so far. Let me just continue and kind of speed through the rest of this. Okay, so now we move I over, and now we're going to be looking at -3, 5, and 3. So first we should check, is there anything in this deck which is not supposed to be in the window range that we're looking at? Nope, we only have the 5, and the 5 is in fact within our range of 3. So then we're going to try to process the current element that we're on, which is 3. So first, before we put the 3 in there, is there anything, is the element before it in the deck, is that less than 3? No, it's not. So our order of the decreasing deck is preserved, so that's fine. And then we should also output the max number, the first element in the deck as well. So that's why we have 5 here. Okay, so then we move I over, and then now we're going to do the same thing. So our new window is 5, 3, 6. So we check, is there anything that doesn't belong in this? Is there anything in the deck which is actually falling outside of this window range? Nope, so we're fine. So then we're going to try to put the 6 in there, but before we put the 6 into our deck, is there anything, is the back of the deck currently less than our current number we want to process? It is, so we need to remove the 3 before we put the 6 on there. Oh wait, but then we continue looking and see that the 5 is also less than the 6, so then we have to remove the 5 as well in order to maintain the property of a decreasing deck. So let's just look at that again and see if that's right. So yes, 6 is at the beginning of the deck because 6 is the largest element in this window, 5, 3, 6, right? So then we'll output 6 into our output, and then we move I over. Now I is here at the very last element, and now we're representing the window of 3, 6, 7. And so first we want to check, is there any element in the deck which falls outside of the range of this window of 3, 6, 7? Nope. So we're good to go there. But then before we put the 7 into our deck, we need to check, is the previous element less than our current element? It is, so we have to remove that before we put in the 7. So now the deck is in decreasing order, and now we can output the 7, which is whatever is at the front of the deck. Okay, so that is how it worked for the first problem. Now I'm going to do a quick example with another example that I just made up. So at the beginning of the deck, we always just put in the first element. The decreasing order is maintained, so that's good. And then we won't output until we've reached a window of size 3, right? So nothing to output yet. So then we move I over, and then now first thing we want to check is if there's anything that falls outside of the range of this window. Does the deck contain any element that falls outside of the range that we're looking at? So nope. So then we're going to try to put in the -5, but before we put in the -5, is the element at the back of the deck, is that less than -5? No, it's not. So we can put in -5 directly. So the decreasing order is maintained. Move the I over, and then now we're looking at the window of 10, -5, -2. So yep, first thing we want to do is check if there's anything outside of this window that's currently in the deck. No, there is not. So then we try to put the -2 on there, but before we put the -2, we see is the number at the back of the deck, is it less than -2? Yes, it actually is. So we have to remove this -5 before we put the -2 on there, so that we maintain a decreasing order for the deck. And so now we will output whatever's at the front of the deck, which is 10, and then we'll continue to keep moving. Okay, so now we're representing the window -5, -2, and 4. And yeah, so let's see, is there any element in the deck which falls outside of this range of outside of this window range? Oh yes, there is. So we have to actually remove this 10 from the deck before we do anything else. And then next thing on our list is to try to put the 4 in there. But before we put the 4 in there, we have to look at the back of the deck and see if there's anything that's less than it. Oh, we found that the -2 is less than our current number, so we have to remove that before we actually put the 4 in there. So now we've completed this iteration, and our current maximum in this window is 4, so that's why we output 4 here. Move the I over, and then now we're representing the window of -2, 4, and 0. And then so now is there anything in the deck that falls outside of this range of numbers and range of indices, whatever? No, there is not. So we'll try to process the 0 and put it in the deck. And but before we put the 0 in there, is there anything at the back of the deck which is less than 0? No, there's not. So we can put 0 in there, and our decreasing order is maintained. And then yep, so then we'll just output whatever's at the front of the deck, which is 4, and then move our pointer up. So now we're representing the window of 403, and now let's see, is there anything in the deck that is outside of the range of these indices? No, there's not. So we're good to go. So we can try to place the 3 into our deck. And let's see, so is there anything at the back, starting from the back of the deck, that is less than 3? Oh, there is. So we need to remove the 0, and then we compare the 4 with the 3, and so 3 is not so 4 is not less than the current number we're looking at, so we don't remove the 4, and then we just put the 3 down. So now our decreasing order is maintained, and then we'll output the 4. So if we look at this again and just double check it, the max number in this window is 10, max number in this window is 4, max number in this window is 4, and max number in this window is 4. So that looks good to me. Now, alright, so that is the algorithm. Hopefully you guys understand that. I'm sorry it took so long. Just try your best to implement that. I've written the 2 main cases up here. Basically, first, you want to remove anything that is, not in the range, not in your current window range. Removes anything that isn't in your current window range. And then after that, then you can try to, insert the current number into the back of the deck, but first you need to remove all elements less than it before inserting. And then once you do that, then at the end of each iteration, you should append to your output array. Yep. Alright, so good luck. Try to implement this now. I'll have the code in the description, and Yep, thanks for watching.